All right, example 3, we've got a cylinder. We want to find the height and the radius of the least expensive closed cylinder. So it means it has a top and a bottom. Least expensive, so we're minimizing cost, which has a volume of 1,000. Assume the materials are free, but it costs 80 cents per inch to weld the top and the bottom. So you have to weld the circle onto the bottom, you have to weld a circle onto the top, and then you have to weld a seam along the side. Okay, so for minimizing cost, we are going to write a cost equation. I'm going to say the height of the cylinder is h, and we'll say the radius of the circle on the bottom is r. So the cost of this welding is going to be 80 cents times the height plus 80 cents times all the way around 2 circles. The circumference of a circle is 2 pi r. So that's the distance around one circle. The distance around 2 circles would be 4 pi r. Okay, so my cost equation is 0.8 h plus 3.2 pi r. Now, just like in the previous problems, our cost equation has 2 variables. We need to get this in terms of 1 variable. So we have to write a second equation. They give us another piece of information. They say volume is 1,000. And so the volume of this cylinder would be the area of the bottom, pi r squared, times the height of the cylinder, and that has to equal 1,000. I'm going to take this equation and solve it for h, and I end up getting h equals 1,000 divided by pi r squared. I plug that in for h into my cost equation, and let's see, I'm left with cost equals 800 divided by pi, I'm going to call that an r to the negative 2, plus 3.2 pi r. So now I have cost in terms of 1 variable only. The next thing we're going to do, step 3, is find all critical points. So I have to find the derivative of this equation. Negative 2 times 800 would be negative 1,600 over pi, r to the negative 3, and then plus 3.2 pi. I'm going to take this derivative, set it equal to 0, and solve. And I think I'm going to add that negative 1,600 over pi, r to the negative 3 to move it to the other side. So now I've got 3.2 pi equals 1,600 over pi r to the 3rd. I multiply both sides by pi r to the 3rd. So 3.2 pi squared r to the 3rd equals 1,600. r to the 3rd is whatever 1,600 divided by 3.2 times pi is. I put that into my calculator, and I got approximately 50.66. So r would be the cube root of that number, which is approximately 3.7. Now step 4, I need to make sure, is this actually a minimum or is it a maximum? I'm going to use my first derivative test. My critical point is 3.7. And so I'm going to pick a number smaller than 3.7, like 1. I'm going to pick a number bigger than 3.7, like 4. And I'm going to plug those numbers into my first derivative. So this thing right here. I used a calculator to do this for me, and I ended up getting a first derivative that was negative, and then a first derivative that was positive. So the function is decreasing, then increasing. That's a good thing. That tells me that this is a minimum, and that's what I wanted to find. Finally, they want the dimensions, and so I just figured out r is 3.7 inches. To find the height, I'm going to take the 3.7 and plug it into my expression for h. So 1,000 divided by pi times 3.7 squared. I put that into a calculator and got 23.3 inches. All right, my last example has to do with the concept of economic lot size. And this is basically the idea of how often should a company be producing a product in order to minimize its costs while still meeting the customer's demands. So imagine that this company decides to produce 12,000 items a year. You could imagine over the course of 1 year, their inventory might look something like this graph. They produce all 12,000 items, say in January, and then they slowly decline and they run out of things after 1 year and have to reproduce the 12,000 items. In this case, their production costs would be a little lower because they're only doing the production once a year, but they would need to have a larger warehouse, and so their warehouse costs would be a little bit higher. Now, another option we could imagine is this company could produce 1,000 items every month. They still would be producing 12,000 items a year, but they'd be making it in 12 different batches. This would give them high production costs because they're doing their production 12 times a year, but they wouldn't need as large of a warehouse. They'd have smaller storage costs. And so our question is, well, what should they do? How often should they be producing their items? And that idea is the economic lot size. So I'm going to derive a formula for you, but first I'm going to give you our variables. We are going to say Q is the number of units per batch, and that is our variable. That's what we're solving for. Our constants, K will be the cost of storage, 1 unit for 1 year. F is a fixed cost to manufacture the product, so you could think of it as like a setup cost. Whereas G is the cost of manufacturing 1 unit or per unit. And M will be the total number of units produced annually. So it turns out we can write the following formula, following function, that gives the total production cost. Very quickly, where does this come from? The first 2 terms describe my manufacturing cost. This first term is kind of like the setup cost. And then the second term is basically the cost per item of manufacturing. The last term here is going to be my storage cost. We're basically saying that the cost of storage is going to be that constant K times our average inventory, which is the Q divided by 2. I'm happy to explain in more detail where these terms come from, but I'm not going to take the time to do that in this video. So send me an email if you want to know where exactly each of these terms come from. The thing I wanted to show you is if this is a function for total cost, how do we find the Q that gives us a minimum cost? Well, we have to find the derivative of this thing. And to find the derivative, we need to remember that our variable is Q. Everything else is a constant in this function. So the only variables are those Q's. Everything else is a constant. So for the first term, the F and the M are constants. Q to the negative 1 is my variable. So my derivative would be negative Fm Q to the negative 2. Gm is a constant. The derivative is 0. And the last term, K over 2 times Q, the derivative is the K over 2. I'm going to take this derivative, set it equal to 0. I'll add that negative term to both sides to move it to the other side. So K over 2 equals Fm over Q squared. I wrote that Q to the negative 2 as a 1 over Q squared. I'm going to multiply both sides by the LCD. This allows me to cancel 2's on the left and Q squareds on the right. So now I've got Q squared times K equals 2Fm, or Q squared equals 2Fm divided by K. So Q would equal the square root of 2FM divided by K. And so this is the number of items you should produce per batch in order to minimize the storage cost. All right, so let's do an example. So first thing we're going to have to do is kind of pull out the important variables in this problem. So let's see, a paint company has a steady annual demand of 18,000 cans of paint. That needs to be my total annual production. My M is 18,000. The storage cost is $3 per can. So K, storage cost is 3. And it costs $7.50 to set up the plant for production. That's my fixed cost. Every time I produce, I have to spend $7.50. Find the number of cans of paint that should be produced in each batch, as well as the number of batches per year in order to minimize the total production cost. Well, to find the number of cans in each batch, I am going to use that formula that I just derived for you guys. So I am going to plug in some numbers. We said F is 750, M is 18,000, and K is 3. And when I put that into my calculator, I ended up getting 3,000. And so this tells me I need 3,000 cans. And so this tells me I need 3,000 cans per batch. And if I need 18,000 cans total, well, 18,000 divided by 3,000 means we're going to have to produce 6 batches per year in order to give us a number of products. All right, that's it for this section. I know these problems can be challenging. They really just take practice. And so don't forget, you can use tutors in the math lab, or you can always come to office hours if you need more help.